Hi guys, welcome to Amateur Chemistry. So, nitric acid. I am sure most of you know just how useful and important this chemical is, and I am not talking on an industrial level, but even in the amateur chemistry lab. Nitric acid is what allows chemists to perform thousands of amazing reactions, from the famous nitration to making colorful nitrate salts or refining precious metals, among some flashier things. There is no doubt that every chemist needs this stuff in their lab, and what's quite sad is that it's often impossible to get. That, however, doesn't stop people from just making nitric acid themselves, often from seemingly unrelated things, a prime example of which are some of my older videos where I made nitric acid from fertilizer or even wood. There are hundreds of other methods documented by many amazing chemists here on YouTube, and if all you want is some concentrated nitric acid for experiments, they are all fine. If you are like me, however, and got bored of watching the same thing be done over and over, I have good news for you, since for a while I've been wondering what 100% nitric acid is like. You see, the thing with nitric acid is that its properties heavily depend on its concentration, and while the dilute stuff isn't really dangerous, pure nitric acid is, let's just say, scary, and even professional chemists often refuse to work with this deadly component of rocket fuel. That's exactly why I decided to make it, and since pretty much nobody made and tested pure anhydrous nitric acid on YouTube before, I was really eager to see if the crazy stories about it are true, and if I could unlock some new potential of this seemingly well-known reagent. Now, before I start putting my safety gear to the test, I have to warn you about just how deadly and dangerous the stuff you are about to see is. Concentrated nitric acid is not only really toxic, but a stupendously powerful oxidizer capable of easily setting most lab gloves on fire while generating copious amounts of the incredibly deadly nitrogen dioxide gas, which when entering your lungs basically turns them into mush. That's why you should never mess with nitric acid at home, and I am doing this only because through years of chemistry experience I've built up enough safety precautions to deal with such deadly chemicals, and this video is not a tutorial and is for educational/demonstration purposes only. With this out of the way, I can start whipping up some real strong acid, and to truly show you what it means to have pure nitric acid, I figured that I would first start small and make some weaker stuff you might normally find in a lab. The first nitric acid that many chemists make is what I call poor man's nitric acid, and as this name suggests, it's quite dilute and kind of dirty. It can be a substitute for concentrated nitric acid in many experiments, and it's what I used to make a long time ago. The ingredients that I will need are actually the same ones I will use for making all the other quote-unquote levels of nitric acid, and they are sulfuric acid and potassium nitrate. Mixing them is the best and cheapest way to obtain various concentrations of nitric acid, and for my poor man's stuff I wanted to use 90 grams of concentrated sulfuric acid diluted with roughly 200 milliliters of distilled water. The water will really ease the synthesis, and instead of using it as a liquid, I resorted to using ice, since cooling the sulfuric acid is quite necessary as it generates a bunch of heat when mixed with water. With my cooled sulfuric acid solution ready, I could now start adding in 100 grams of potassium nitrate, which started rapidly dissolving. In doing so, it reacts with sulfuric acid present in the solution to form my precious nitric acid and a salt called potassium bisulfate. This reaction happens only because sulfuric acid is much more chemically potent than nitric acid, easily liberating it from many nitrate salts. After adding all the potassium nitrate, I now wanted to forcefully drive this reaction to completion, for which I got everything onto a hot plate and turned on the heating. This quickly made all the undissolved nitrate go into solution, and now with the reaction complete, I wanted to remove some of the potassium bisulfate byproduct, for which I put the beaker into a fridge. This made a part of the bisulfate crash out as these small crystals, which I was able to easily remove by vacuum filtration, leaving me with some clear, dilute nitric acid. Now, since there is still a good bit of potassium bisulfate in it, I can't really calculate my yield or its concentration. However, from my experience, the yield should be around 90%, and based on the amount of water that I used, this gives a roughly 25% solution. As you can see, this acid is far from perfect, being only visually clean and incredibly weak. I mean, it doesn't even light my gloves on fire, so I think that for the next batch I can do a little better. This second level of nitric acid is what you most commonly find in a real lab, since it is both concentrated and safe enough to be used for pretty much every reaction requiring nitric acid. It's called azeotropic nitric acid, and I'll explain what that means in just a minute. Its concentration is usually around 68%, and since it has almost 3 times more acid than the poor man's stuff, you can probably guess that it's way more fun. Making it is also strangely straightforward. However, as with every new level of nitric acid, it requires quite a bit more glassware and equipment, which is kind of similar to how you would unlock a new chapter in a game. If you think about it, chemistry is kind of like a game where you actually die when you screw up, and each new level of danger requires more sophisticated equipment and techniques, and to quote-unquote unlock more concentrated nitric acid, I began by choosing this flask as my reaction vessel. This time I added the potassium nitrate first and used 330 grams. In terms of sulfuric acid, I chilled 340 grams of it in a freezer and had to dilute it with around 100 milliliters of distilled water. Similarly to before, I used ice, and even though everything was initially well below zero, the resulting solution was nearly boiling. I let it sit for a few hours to cool down a little, and then just dumped it all into the flask from before. I then assembled it into this simple distillation apparatus, which will allow me to remove nitric acid from the flask as it forms, greatly increasing its purity and concentration. After just a while of heating, the mixture began taking on an orange-brown color, and this signals that nitric acid is being produced, since when it's heated and concentrated enough, it easily breaks down into nitrogen dioxide gas, which is brown. This spicy air quickly filled the whole apparatus, and it's one of the main reasons why I am doing all this in a fume hood, since breathing this stuff in equals permanent lung damage. Anyway, as the flask warmed up, all the potassium nitrate dissolved and the resulting solution began to boil. Its vapors quickly traveled to the condenser, where they turned back into a liquid which then dripped into a receiving flask. Now, this liquid is actually a mixture of nitric acid and water and boils at 121 degrees Celsius, which is 21 degrees above water's boiling point and a whopping 38 degrees above nitric acid's boiling point. It contains roughly 68% nitric acid by weight and is the so-called azeotrope I talked about earlier. Its formation makes obtaining 68% nitric acid very convenient, but it also means that you can't really obtain any stronger stuff by conventional distillation. That's why I will have to use some special tricks to go up to 100% nitric acid, and to finish preparing this one, I just waited for the distillation to complete, and when no more liquid was coming over, I turned off the heating and collected my product. I ended up with quite a bit of it, which was really cool, and since this time it's just a mixture of nitric acid and water, I could actually test my product's concentration. This can be done by measuring its density and using this handy-dandy online chart, which told me that the acid I made wasn't quite the 68% I hoped for, but instead sat around 60%, which is probably due to me using a little too much water and not redistilling it. It should still be alright, however, and its reactivity is pretty much exactly that of the azeotrope, meaning that it still can't set lab gloves on fire, but starts to make them burn faster. This nicely showcases how water has this kind of a dampening effect on nitric acid, and its removal really allows this acid's chemical aggression to shine. Speaking of chemical aggression, I think it's time to move on into the more uncharted territory of nitric acid concentration and remove pretty much all the water from it. This will result in something called red fuming nitric acid, or RFNA for short, and much like the azeotrope, I will explain this name in a minute. The most important thing about RFNA is that it's considerably scarier than the azeotrope and, as expected, requires quite a bit of preparation to make. This basically means that I have to take extra care in excluding all the water from the reaction, and the best place to start is by drying the potassium nitrate. This seemingly dry powder has quite a bit of water in it, and to get rid of it I got some into a baking tray and roasted the hell out of it using my trusty oven. This made it visibly drier, not forming any lumps, which was very good, and to start making extra spicy nitric acid, I got 400 grams of the dry potassium nitrate into a flask. I then followed this up with 420 grams of chilled sulfuric acid and assembled the flask into a simple distillation setup much like before. This time I could really tell that I was working with some strong nitric acid since the amount of nitrogen dioxide generated was quite crazy. There were also these very cool rings of white fumes coming out of the apparatus, and this is the fuming part of red fuming nitric acid since at such high concentrations it likes to attack moisture from the air, producing these incredibly corrosive acid fumes. Anyway, the distillation seemed to go way faster than before, probably because of pure nitric acid's low boiling point, and it didn't take long for the vapors to stop coming over. In the end, I was left with a good bit of some clear apple juice looking liquid, which is pretty much pure nitric acid. It still isn't completely pure though, since there is quite a bit of nitrogen dioxide dissolved in it, giving it this reddish tint which solves the remaining mystery of its name. To make the final level of nitric acid in this video, I will have to figure out how to remove the nitrogen dioxide as well as all traces of water, however for now I don't need to care about that. To finish preparing the RFNA, I measured its concentration using the exact same method as before, and it came out to be around 99%, which was quite astonishing. I mean, keeping water out of the reaction really paid off, since this acid is virtually dry and you can really tell because of how it reacts with my gloves. This spontaneous combustion is why I avoid using gloves when handling pure nitric acid throughout this video, and it's so corrosive that virtually the only way of storing it is in a glass bottle with a Teflon tape sealed lid. You might notice that I have quite a bit more of this acid than what I just made, and that's because I actually had some left over from a long time ago and just decided to combine the two, especially since I will use a great chunk of this stuff to make the anhydrous nitric acid. Speaking of anhydrous nitric acid, I was really curious if getting that last percent of purity was going to make it that much angrier, and I suppose that there is only one way to find out. The tricky thing about making anhydrous nitric acid is that there are pretty much no sources on it anywhere, and at this point in the project I was feeling kind of unsure if I would succeed. I mean, I could use something like the incredibly expensive phosphorus pentoxide to chemically react all the water away, however I would then have to distill the dry nitric acid off, and this would mean losing a ton of it to decomposition. For some time I kind of lost hope of obtaining completely pure nitric acid, but then one day I stumbled upon this US patent from 1975 about doing just that. I mean, it looked too good to be true, claiming to achieve anhydrous nitric acid using really simple chemistry, so logically I was quite eager to try it out. First, it called for using this cool piece of glassware called a separatory funnel, which I was to fill with some fuming nitric acid. I chose to use just 50 ml since I didn't really know if this whole thing would work, and I prefer not to work with too much rocket fuel grade nitric acid at a time. To remove all water from nitric acid, the patent called for the addition of roughly half its volume in concentrated sulfuric acid. The two acids easily combine, and since sulfuric acid really loves water, it basically steals it from everything, including nitric acid. Now, the whole thing about the patent is how you go about separating the anhydrous nitric acid from this corrosive mixture, since, as I said, distillation isn't really an option. You see, it turns out that the very common lab solvent dichloromethane can actually dissolve nitric acid while leaving sulfuric acid untouched, and indeed, upon adding 50 ml of dichloromethane into the funnel, a new layer appeared. To force the nitric acid into it, I aggressively shook the funnel and then waited for the layers to separate again. I drained off the lower sulfuric acid one and got my precious anhydrous nitric acid solution into a flask. To squeeze out more nitric acid from the remaining mixture, I again washed it with 50 ml of dichloromethane and combined the resulting extract with the stuff in the flask. The dichloromethane in it should contain pretty much all the nitric acid I started with in a completely anhydrous state, and to get rid of the dichloromethane I just have to boil it out. First, however, I wanted to remove this weird cloudiness from the solution, which probably came from some suspended sulfuric acid droplets. I tried to use anhydrous sodium sulfate, which should stick to the sulfuric acid and is like the only thing not to react with this liquid death. After a few hours, all the cloudiness disappeared, which was very nice, and to start removing the dichloromethane, I poured everything into a different flask. I then set it up for yet another distillation, this time using a hot water bath to warm my nitric acid ever so gently. Well, maybe not so gently, since right after adding the hot water, a bunch of nitrogen dioxide appeared and the dichloromethane started vigorously boiling since it has a boiling point of just 40 degrees Celsius. Even though this whole thing looked quite chaotic, it really wasn't that bad, since the nitric acid decomposed just a bit and didn't even begin to boil. After a few minutes, most of the nitrogen dioxide disappeared, which meant that my acid was no longer decomposing and the dichloromethane was boiling away quite steadily. When all of it was gone, nitrogen dioxide started to appear again, which was a good indicator to stop the distillation. In the end, it left me with this rather small amount of anhydrous nitric acid, which wasn't quite the 50 ml I started with, and if I were to do this again, I would definitely use some more dichloromethane. Anyway, now that I have removed all the water from my nitric acid, I have to do just one final thing to make the ultimate forbidden water, and that is to get rid of all the dissolved nitrogen dioxide. There are a few ways to do this, but the best one in my case is using this really old ozone generator, which, while originally meant for food and disinfection, will now help me make the world's strongest nitric acid. You see, the ozone gas it generates is much more chemically angry than even pure nitric acid, and when I use a calcium chloride filled wash bottle to try it and then lead it to my anhydrous nitric acid, it slowly reacts with any nitrogen dioxide present to form even more nitric acid. In doing so, it scavenges the last minute traces of water, and after roughly an hour of bubbling ozonated air through my nitric acid while keeping everything cool, the yellow color disappeared. This means that I successfully removed all water and nitrogen dioxide from the red fuming nitric acid, making almost perfectly pure white fuming nitric acid. Now, it's not 100% concentrated, since like all chemicals it physically can't be, but doing all this work managed to remove so many contaminants, it's probably like 99.999% pure, and I might as well round it up to 100. It's really funny to think that this small amount of what looks like water is actually one of the strongest acids in its pure state, and since I finally achieved this holy grail of amateur chemistry, now it's time to do some experiments and compare it to all the previous levels of nitric acid I made. First of all, this devil's water is definitely way more unstable than its predecessors, quickly going yellow without the ozone, which is why I had to be really fast with filming all the experiments, and for the first one I just had to see what it does to nitrile gloves. As expected, pouring it over a glove instantly resulted in a big fireball, and you can actually see the difference compared to igniting gloves with RFNA, which takes quite a while. I also recorded this cool slow-mo shot of pouring anhydrous nitric acid over gloves, and this way you can nicely see the evolution of nitrogen dioxide gas and a ton of this white smoke. Moving on, the second reaction I wanted to showcase is how nitric acid interacts with iron in the form of this steel wool. Now, what is really quite interesting, dilute nitric acid dissolves it quite readily, and the azeotropic stuff just eats through it, while RFNA and anhydrous nitric acid don't seem to react at all. This is because when nitric acid contacts iron, a very thin coat of iron nitrate forms around the metal, and when there is enough water present it dissolves, exposing more metal to corrosion. When there is no or very little water present, the iron nitrate coating acts as a protective layer against attack, and this is why nitric acid is often transported in steel tanks. What's quite peculiar about this protective nitrate coat, however, is that at high temperatures, nitric acid just says no to it and explosively oxidizes it and the iron metal beneath to form iron oxide. This also creates enormous clouds of nitrogen dioxide and generates enough heat to melt everything into these glowing blobs. Again, I think that anhydrous nitric acid performs quite a bit better when compared to RFNA, and the slow-mo shot of this reaction is just gorgeous. This protective nitrate coat formation not only applies to iron, and other metals like copper also resist reacting with anhydrous nitric acid. This also proves that the acid I made is really anhydrous, since the addition of just a tiny bit of water causes it to violently react with the copper. The same cannot be said for RFNA, which has enough water to react with copper by itself to some extent, proving that even 1% of water can drastically change nitric acid's properties. Anyway, for the next experiment, I decided to go with a classic and showcase the rocket fuel part of nitric acid, which, being a very strong oxidizer, easily reacts even with weak reducing agents like aniline. As you can see, the two generate this weird tar on contact and let off a ton of gas, which sometimes self-ignites, creating this funny sound. This is known as a hypergolic reaction, where the fuel and oxidizer ignite spontaneously on contact, and reactions like these using pure nitric acid and some more exotic chemicals than aniline are the basis of many liquid propellant rockets. When I tried this reaction with RFNA, it also formed a bunch of tar, but didn't really want to ignite, and the azeotropic nitric acid barely did anything to the aniline, turning it light brown. What's quite interesting is that the poor man's nitric acid seemed to react quite differently, forming this white precipitate, and this is because, being so dilute, it can calmly react with aniline to form a salt called aniline nitrate. Overall, I think that this project really turned out cool, and it was certainly nice to explore the less known aspects of nitric acid, and it also made for a nice starting point for future projects where I will be able to use all the different grades of nitric acid I made. Speaking of future projects, for the last month I have been hard at work at recording my most complicated video to date, and the organic chemistry in it nearly broke me, so while I set out on a long mental healing and editing session, I hope you all enjoyed this video, which I made as a kind of a break between some gigantic projects. If you'd like to support all the crazy stuff I do, please consider subscribing, liking the video and sharing it with a friend, and if you want to directly contribute to improving my content, as well as have access to a lot of ad-free exclusive videos like my lab tour, I invite you to become a patron. My patrons provide most of the funds as well as a ton of motivation for me to keep coming up and recording all these projects, and I want to dearly thank each and every one of them for their generous support. Anyway, big thanks for watching and see you all in the next video.